last topic of differential control volumes. And what I want to do is to generalize from the 1D analysis we have done to 3D. And it's going to be very quick because I'm not going to do it formally, but by analogy. All right. I have just updated the differential control volumes notes with a little bit of an introduction that is going to be useful. So if you have downloaded it, please check out the latest version that is more or less the same. I think it's a little bit better. So we did see all these things. The standard analysis for differential control volumes in 3D is to make a cube like I did here. And this comes from the old notes. And this is kind of a tedious exercise because we're accounting for heat in and out in all of the 6 phases of this differential cube. This is the most general case from the point of view of geometries. However, this most differential case doesn't account for things like advection. and here we come to this conclusion where you get to see this notation of using the Laplacian operator, right? This is one way of arriving to this final equation that we have here, which we will be using today. So this is one formal way. It doesn't account for advection, but accounts for all the 6 phases. Now, there is another way of doing it. And this way is so cool because in 3 lines, you get the whole derivation. The catch is that we used to have the Gaussian integral. Because we're doing enough with the differential equations, I don't want to bring that to the table, but I included it here. So you just see how the very tedious work can be done very simple with some of these things like this Gauss theorem we learn in Calc 2, right? And we end up with the same equation. Okay, so in this case, we have the heat diffusion, what we have in this first line. We saw exactly how to get this by doing a differential control volume, an energy balance, putting the heat transfer mechanisms, including conduction. And the only one thing that was different than lumped capacitance is that now we did an expansion between x and x plus dx because the control volume was very small in the x direction. And when we did this, after some rearrangement, but no simplification or anything like that, we ended up with this equation here, right? In which we have the idea here when we see these equations is not just see them holistically, is to have them talk to us. And what does this equation say? Well, this equation has one term here, another term here on the left. On the right has another 2 terms, this one here and this on the right. And each term has a function. The function of the first term is the transient term. You see, it's variations of temperature with time. The second term has a velocity term. This is advection. The third term has thermal conductivity. This is conduction. And in this case, you see we have a derivative of something in parentheses that has k times a derivative. In this case, we're accounting even for the case in which the thermal conductivity is not constant, although we typically are going to say this. And then the fourth term on the right is the volumetric heat generation that can be Joule heating, viscous heating, radioactivity, can be chemical reactions happening and exothermal chemical reactions. So we have pretty much everything here. We saw how to derive this. For the linear case, and I want to generalize it for the linear case because otherwise it becomes quite painful. But for the linear case, we have the first term is the same, that is the heating or cooling rate. The second term is the same because it depended on the velocity. The third term that depended on conduction, if I take K from up here, I take it out because it's constant, then it becomes a second derivative. And the fourth term is the same. Now, I'm going to generalize this by analogy from 1D to 3D. Of course, doing a little q, infinitesimal q, we can do it formally. I don't see that much value in doing that formal exercise, but after having done it in 1D, I'm going to change it to 3D. And what is the analogy? Velocity is a vector. Similarly, gradient is a vector in reality, and I'm going to write them properly. So instead of velocity times derivative, I'm going to write velocity vector dot product the gradient, and this gradient has this expression that we see here, and this comes from vector calculus that you had, and you probably wonder, what's the story with this? What is this good for? Well, it's good for this. And the beauty of this is that although the equations we're working with might seem complex to you, they're still very simplified because they're 1D equations. When you go to a finite element package in the computer, when you do some sort of analysis for which you can pay big bucks to a consultant, or maybe you're the consultant yourself, you're likely to be using the 3D case. And for the 3D case, you need to use these gradients and Laplacians. So that's why I wanted to share this with you, because this equation that has more mathematical complexity is what is embedded in the computers. So here we have the velocity as a vector that has a component in x, in y, and in z. This is in Cartesian coordinates. And here's the gradient that is the derivative in x, the derivative in y, and the derivative in z, each on its own unit vectors. Right, when I multiply these two, we end up with this component here. Similarly, and this comes from your vector calculus class, when you have a Laplacian of temperature, that, here the second derivative is this thing here. That is the gradient of the gradient, which we write like this Laplacian, like nabla square, and has this expression, second derivative in x plus second derivative in y plus second derivative in z. If I replace these two expressions that I just dragged these concepts of vector calculus to extend my 1D analysis we have done together, we end up with this equation that looks a lot more complex than before. But this equation, when it speaks to us, it says the same thing. And this equation, where it comes from, is the same place. Now, this, instead of making like one bar as we have done so far, that was so convenient, now we're using one element little cube. And we could have done pages upon pages of the little cube and end up exactly here. If we don't account for advection, I have included it in the previous section in the notes. I will not, and I cannot ask you to do that derivation, especially now that everything is online. But you have it, and as you do it, you feel the power of generating your own differential equation. Let's see what this equation tells us. This equation has 8 terms. 8 terms, that's a lot. But the 8 terms coming in groups. Term number 1 is the transient. This we know. It talks to us. It says, oh, I'm the derivative with time. Therefore, my mission in life is to account for transients. And if I have a steady state system, I know that this term is going to go away. term number 2, 3, and 4. And these three are velocity times a derivative of temperature. These three terms account for advection. Velocity times temperature variation, advection. And if I wanted to make it like a finer point, I could say, aha, this is advection in X, this is advection in Y, and this is advection in Z. The physics are the same, but the geometry might play a role now. So we went from term 1 to 4 with this equation talking to us, telling us this is who we are and this is what we do. And if there is no advection in Y, this term would go away. Why might we have no advection in Y? Maybe there is no gradient in Y, then it's 0. Maybe there is no velocity in Y, then it's 0. For example, in the case of heat exchangers, the flow is lengthwise in a pipe. So lengthwise, we have advection. But across a section, we don't have a flow, right? We have like a tube. All the flow moves in the length direction of the pipe. So in that case, we can have a lot of advection longitudinally and 0 advection transversely. All this comes with doing no math, but just reading this the way we would read a book. Terms 5, 6, and 7. I grouped them up here, and they have the thermal diffusivity in front. I know what they are. They're the conduction, right? Alpha is K over rho Cp, K over rho C. So this is thermal conductivity. In this case, this equation is good only for constant thermal properties. And here we go. We have now these three terms, all three are conduction. And if we wanted to make a finer point, we can say, aha, this is conduction in X, conduction in Y, and conduction in Z. Now, this is Cartesian coordinates, right? But let's go back to thinking about heat exchangers. In heat exchangers, we said we have flow lengthwise, and actually we looked twice at the Peclet number to see that in pretty much all cases, lengthwise advection dominates enormously over conduction. And so if X is the direction of the pipe, I can forget about my term of conduction in the length direction. However, we said there is no velocity that is transverse because everything flows in a pipe. So if we have no transverse velocity, we would have no advection in Y. And this term of conduction in Y becomes very relevant. And without doing any math, this equation starts to speak to us and to say what terms we can take away and not. We can do more. I haven't talked about turbulence yet, and we will talk plenty about turbulence later. In turbulence, you have 3D motion. Even if inside the pipe, you're moving lengthwise in average, locally, you have a 3D motion that is due to turbulence. And guess what? Then we could say, aha, then I cannot neglect this advection here. And it's true. But if you remember, you can do some trick on these Navier-Stokes equations such that you go back to the standard Navier-Stokes equation plus an additional term that accounts for turbulence. And typically the way you do with that is with some sort of an enhancement, trying to guess what this extra term is. Right, and it all comes in this equation. Before we go crazy with mathematical solutions to the differential equation, this is telling us what goes or doesn't go. And finally, term number 8 is the heat generated, same as before. I wanted to show you this, so you have the most, as long as we assume constant material properties, this is the the most general equation of heat transfer that accounts for advection, conduction, heat generation, transient, right? Viscosity. What do you want? We got it, right? And going back to this Peclet number, which we discussed earlier twice in 2 different days, if my Peclet number is large, that means the fluid is dominated by advection. So in that direction, I know that in the direction of advection, I can cross over, I can take out the conduction terms. Conversely, if the Peclet number is small, the fluid is, the system is dominated by conduction, and I can take out the advection terms. So this enormous equation is something on which is like a blank sheet of paper. This equation says so much and says nothing at the same time. In this blank sheet of paper, we can write whatever we want. And here, on this equation, we can say, we account for a system in which conduction dominates, or advection dominates, or advection dominates in the length of the pipe, but conduction dominates across. It all comes from seeing this equation. This is what I wanted to share with you here. I will switch now to the topic for this week. And as I switch, if anybody has any questions, please put them on the chat, and I'll do my best to address them. And if not, if you can come up with a question later, we can discuss it at the office hours today or on Friday, or you send me an email and we try to schedule another time that might be good for all involved.